Hello and welcome to this 9th lesson in this series on metric and topological spaces. In this lesson, we're going to be looking at how to take old topological spaces and create new ones. And as always, in the description is the link to the booklet for you to follow along with, and that has homework questions in. Okay, so the first type of topological space we can create is the subspace topology. So if x tau is a topological space and y is a subset of x, then we can define a subspace topology. And we define this by saying O is open in the subspace topology, so that is O is in tau y, if and only if O can be written as U intersect y, where U is open in x. And we could say something similar for closed sets. So something is closed in the subspace topology if it can be written as something closed intersect y. So just because we've called this the subspace topology, that doesn't mean it is a topology. We need to check that it obeys all the axioms of a topological space. So firstly, are the empty set is the empty set open and is y itself open? So let's have a think. Well, the empty set is the empty set intersect y, which is something open intersect y, so that is open. Similarly, y can be written as x intersect y, and x is open, so the intersection here is open. Then, for the arbitrary union, so firstly, any open set U alpha can be written as an open set intersect y for some open set in the original topology on X. Then if we union all of these U alphas together, well, that's the union of O intersect y, which is the union of all the O's intersect y. However, the union of the O's is already open in X. So this is of the form something open in X, intersect y. Now finally, for the countable intersection, you can have a go on your own. It's very, very similar to the union. Okay, now you've had a go, let's go through how to check that it obeys the countable intersection axiom. So it's the same thing. We say ui is equal to oi intersect y for some open set in the original topology. We intersect all of these, which is the intersection of O intersect y, which we can, just like before, this is the intersection of all the O's intersect y. And the intersections of all the O's is again open, because this is just a countable intersection, and we already know X is a topological space. So if we intersect all of these open sets, it's still open. Okay, so using the topology on a finite set, which is given here, but we've seen it in previous lessons, and a subset Y, which is 1, 2, we need to find the subset topology. So the way to do this is, because this is finite, we can just go through and intersect Y with all of the open sets. So here, the empty set intersect Y is the empty set, X intersect Y is Y, 1 intersect Y is 1, and 2, 3 intersect Y is 2. So we've intersected all the open sets with Y. All of these outcomes are going to be in the topology. So the subspace topology is given here. Okay, for our next example, we've got the real line with the standard topology. Let y equal the closed interval 0, 1. Then are the following open, closed, or neither in the subspace topology. So let's have a look at our first one. Well, we can write this as the intersection of 0.52 and y. I mean, it doesn't have to be 2 there, it could be really any number bigger than 1. And this is of the form open intersect y, so it's open. Okay, Have a go at the next two on your own, and then come back to the video and I'll go through the answers. Okay, now you've had a think, let's go through them. So for this one, we can write this as R intersect Y. So therefore we would think this is open, but also 0, 1 complement 0, 1 is the empty set, which we also know is open. So therefore this is both open and closed. And then finally, we look at the complement of this, and the complement of this can be written as the union of two open intervals intersect Y, and therefore the complement is open, and so it is closed. You could have maybe seen that a bit quicker and shown that it's a closed set intersect Y and therefore must be closed. But we haven't explicitly proven that, even though that would work. Okay, something that often comes up whenever you have a subspace of any kind, not just in topology, is the inclusion map. So if X tau is a topological space and Y is a subset with the subspace topology, we have the inclusion map that goes from Y to X, and it's defined by I of Y as just Y. So it's essentially the identity on that subset, but it is only defined on that subset. So it's not the identity on X, but the identity on X kind of restricted to the subset Y. So we're going to prove that the inclusion map is continuous, and I'm going to go through this proof, and then later on in the video, we're going to see something very similar called the projection map, and then I'm going to ask you to prove that it's continuous, but the proofs are very similar. So we want to show the inverse of open sets is open. So let U be any set that's open in X. Then the pre-image of U is U intersect Y. And then this is open in Y because it's open intersect Y. And therefore it is continuous. Then our theorem. So we have if Z tau prime is a topological space and F is a map from Z to Y, so remember Y is the subspace, well this map is continuous if and only if the inclusion map after F, and this is a map that goes from Z to X, if that composition is continuous. Now the proof for that is in the booklet. We're now going to look at the idea of a basis of a topological space. Now this is a similar idea to linear algebra, where you can write any vector as a sum of elements in the basis. Well, here you can write any open set as a union of sets in the basis. So let X tau be a topological space. A collection of open sets B is called a basis for the topology if every open set can be written as a union of the sets within the basis. And you may remember that we simplified some proofs when looking at metric spaces just by looking at open balls. And that's because we can see here open balls form a basis for the Euclidean topology. And there's really only a couple of useful examples. So firstly is that open balls or intervals are a basis for the standard topology, and single points form a basis for the discrete topology. For the other topologies we've seen, the idea of a basis isn't particularly helpful, but it's very helpful for the standard topology. Okay, for our example, we've got our finite set X is 1, 2, 3 with this topology. In this topology, is this following here a basis? I'll give you a few seconds to think about it, then I'll give you the answer. Okay, so the answer is no, this is not a basis, and that's because the sets 2 and 3 are not individually open. Even though every set in the topology can be made from a union of these, this doesn't work because 2 and 3 are not open. I mean, if this were a basis, it would also imply that sets like 1, 2 and 1, 3 would need to be in the topology, which clearly they're not. So for our next example, we've got a set X that has the elements 1, 2, 3, 4, and you're given the basis, and you're asked to find all the open sets, so find the topology. And this is quite a useful way of specifying a topology. It's easier to specify the basis and then say, well, the topology is that which you can form just by taking all the different unions of the elements in the basis. So have a go on your own of unioning these and seeing what the topology is, and then come back to the video and I'll go through them. Okay, now you've had a think, I'll go through it. Now the first set is the empty set. Now this has to be in the topology, it was one of the axioms, but is maybe a bit strange. How did this come out of a union? Well, the empty set is the union of nothing. But if we're unioning nothing together, well then all of the things in that union are in the basis. I mean, that's kind of trivially true because there's nothing to union, so everything must be in the basis. This is again one of those times where the empty set, it's sometimes a bit confusing or surprising, but it ends up being almost true by default or included by default. Then the other open sets are all the things in the basis. The set X itself, we can just union the things in the basis. And then we do all the other possible combinations of unions. And we get these sets. So our topology would just be all of the sets listed here. And you can check that it is a topology. Then in the booklet, I've written a little paragraph about how to do this more generally. It gets a little bit technical, but you can kind of read through that and think through that after the video. So we're now going to look at the product topology. So if X and Y are topological spaces, and they have the bases Bx and By respectively, then we define the product topology on X cross Y via a new basis. And this new basis is B, and this is all sets of the form O cross U, where O is in Bx and U is in By. And remember that O cross U is the set of pairs of points where the first point is in O and the second point is in U. And at this point you may ask, is it always the case that we can find a basis Bx and By for our topologies tau X and tau Y? And the answer is yes. There's always a trivial basis, which is just the whole topology itself. So if you can't find a nice one that simplifies things, you can always just use the whole topology. And then the proof that this is a topology is in the booklet. I'm going to make a quick little aside before this. Certain properties of the topology are automatically satisfied by a basis. So, for example, the empty set is automatically satisfied and arbitrary unions are automatically satisfied because the basis is, or the topology is defined in terms of unions of the basis. So once we're given a basis, in order to prove it's a topology, we only need to show that the full set, so X cross Y, can be made out of unions in the basis, and we need to show countable intersections of elements in the basis can be made out of elements in the basis. That's in the the paragraph I've written, and then it will be kind of explained in the proof as you go through it. Our first few examples are going to be a bit more conceptual in that I'm just going to ask you to describe the basis. So firstly, we've got two copies of the real line. The first has the discrete topology, and the second has the indiscrete topology. And we want to have a general idea of what the basis looks like for the product space. So how do we do this? So firstly, the basis of the discrete topology is just singular points. Remember here, any set is open and any set is just the union of singular points. Then for the indiscrete topology, the basis is just the real axis. or the real line. So therefore, the basis of the product space is of the form single point times or cross the real axis. Okay, for our next example, we have two copies of the real line, but this time they have the standard topology. So what do the general form of the basis look like in the product space? Okay, have a go on your own and then come back to the video. Okay, now you've had a think. So firstly, recall that the basis of the standard topology is open intervals. And we saw when we did metric spaces that any open set can be written as a union of open intervals. And I briefly mentioned it a couple of slides ago, that the basis of the standard topology is just open intervals. Therefore, the basis of the form open interval cross open interval. And that's just rectangles, where they're open rectangles and so the boundary is not included. And something we will see in a couple of slides' time is that this is equivalent to the Euclidean topology on R squared. Even though these are rectangles and the Euclidean topology is open balls, or in this 2D it'll be circles, we'll show that actually they are equivalent in the sense that what's open in one is open in the other. Okay, now we have the real line with the standard topology, and then another copy of the real line, but this time with the cofinite topology. And the basis for the cofinite topology is just the cofinite topology itself. There's no nice, simpler basis that we can use. So, in the product space are the following: open, closed, or neither. So I'll have a go at the first one. So I've drawn it on the right there. So firstly, we have the open interval, and then there's the single point 5. Well, this is an open set cross a closed set, so it's neither. Okay, have a go at the next few on your own, and then come back to the video. Okay, now you've had a go. All right, so for the next one, the set looks like this. And this is open cross open, and so is open. For the next one, you closed cross closed, so it's closed. Okay, we now want to show that the standard topology on R squared is equivalent to the product topology we saw a couple of slides ago. And the way we're going to do this is to show that the bases are open in the other topology. So the basis of the standard topology is open balls. So we want to show that they're open in the product topology. And the basis of the product topology was the open rectangles. And we want to show that they are open in the standard topology. So I'll do the first one, and then you can do the second one. So let's have a look at the first one. Firstly, we take any point xy inside the open ball. We now want to show that we can fit an open rectangle containing xy inside that open ball. So let's let epsilon equal r take away this square root. And here epsilon is, or this right hand side, is the distance from xy to the circumference. And therefore epsilon is any value smaller than that distance. Therefore, we construct this rectangle on the left, where the rectangle goes from x minus epsilon over root 2 to x plus epsilon over root 2, and the same for y. And this rectangle is open, and it's contained in the open ball. Now, the reason we need the root 2, instead of just saying x minus epsilon, x plus epsilon, is so that way, even if we go at a from the center of the rectangle to the corner, it's going to be, that distance there is still going to be less than the distance from xy to the circumference. It's maybe hard to see when you're just doing this, but do try and draw it out draw an open ball, take a distance epsilon, draw a square, and find the distance from xy to the corners of the square and to the edges of the square. And you'll see that this proof does work out. It's maybe just a bit hard to see straight away here. Okay, now have a go on your own. For the next one, show that the open rectangle is open in the standard topology, and then come back to the video and I'll go through it. Okay, now you've had a go. So firstly, we're going to take any point in the open rectangle. Then we're going to let epsilon be the minimum for all of these. So that is, epsilon is less than the distance to the edge of the rectangle in any direction. So we're looking at the minimum distance from xy to the edge of the rectangle, and epsilon has to be smaller than that. And then B, epsilon is open, because it's by definition an open ball, and it's contained within the rectangle. Therefore, for any point xy, we can find an open ball in the rectangle, and the rectangle must be open. Okay, we're now going to introduce the projection map. So if we have a topological space x cross y, and this is a product space, then the projection map pi x goes from x cross y to x, and it just gives us the x coordinate of our point in xy. Similarly, we could define a y projection map, or if we have multiple products, to whichever coordinate or whatever space we care about. Basically, it just ignores all the other coordinates and just returns the one we want. So for our next exercise, we're going to prove the projection map is continuous. This is very similar from when you looked at the inclusion map. So I want to give you some time to work it out by yourself, and then I'll go through it. Okay, now you've had a go. Firstly, we consider any u open in X. We take the pre-image, and the pre-image of u is u cross y. Remember, no matter what it is in y, it's just going to be ignored. And therefore, this is open. There's open cross open. And therefore, the projection map is continuous. Finally, the thing we're going to introduce is the idea of a homeomorphism. This is not a homomorphism. Homomorphisms, they're kind of similar in the sense that we're looking at when spaces are equivalent in some sense or obey similar properties. Homeomorphism is for topology. Homomorphism is for algebras. So if we have x and y are topological spaces, a map F from x to y is called a homeomorphism if it is continuous and it has a continuous inverse. And in this case, we would call x and y homeomorphic. And when we think here, if F is continuous and has continuous inverse, what that means is if we have an open set in X, it goes to Y, an open set in Y. If we have an open set in Y, it goes to an open set in X. And remember that in order to have an inverse, it must be bijective, so it must be 1-to-1. And this is basically what we're saying is the spaces are topologically equivalent. If two topological spaces are homeomorphic, then everything we look at topologically in one is the same in the other. Okay, so the famous kind of joke amongst topology is that a teacup is a donut. So now we can see in what sense that's true. So we're going to see that it's true in the sense that they are homeomorphic to each other. So let's think of what these might be as topological spaces. Well, they're surfaces in the 3D space. So their topology is the subspace topology coming from the standard topology in R3. So the standard topology on R3, or the basis of that, is open balls. So in order to find what the open sets are, we take an open ball, we intersect it with these, and what we get is an open set. So you see here, I've got open balls, and in red, I've highlighted what the open set would be. So what the intersection of that open ball and these surfaces would be. And these two things are homeomorphic in the sense that we can create a map from the donut to the teacup that is continuous, has a continuous inverse, and maps one of those red open sets to a red open set.